I showed previously how we can calculate beta, or the probability of making a type 2 error. In this screencast, you'll learn about the power of the test, which is closely related to beta. If we have a null hypothesis and an alternate hypothesis, beta is the probability that you will make a type 2 error. In other words, you will fail to detect that the alternate hypothesis is true when in fact it is. And we can calculate beta by the probability that x bar is greater than our critical sample average based upon the alternate hypothesis distribution, which is centered about mu1. So beta is the probability that you will not detect a shift in mean. In other words, if we have a shift in mean, beta is the probability that you won't be able to detect that the alternate hypothesis is other than the null hypothesis. If we subtract beta from 1, this is known as the power of the test. Power is 1 minus beta, and power can be interpreted as the probability of correctly detecting a shift in the mean, if such a shift has actually occurred. The power of the test is shown as this green shaded region, and it also includes alpha. If we go back to a previous example that I worked through, we calculated beta to be 0.36. We can just subtract beta from 1, and that's the power of a test. So beta plus power has to equal 1. Do you think that it would be easier or more difficult to accept the alternate hypothesis if the true mean of ride times were 2.5 minutes as opposed to 2.8 minutes? I've got a simulation here where we have the null hypothesis, which is centered about 3, and I've got a mean shift. The mean shift is basically how far below the null hypothesis the alternate hypothesis is. I've also got an area here where we can change the sample size. We can also change the mean shift, and I've calculated beta and power. I'll post this up on the course website in case you guys want to take a look and interact with this. But basically, you want to try to maximize power. That is the probability that you will correctly identify a shift in mean. In other words, you will accept the alternate hypothesis when it really is true. So if the mean shift that you're trying to detect is bigger, then you see that the power increases. And if we have a really big shift in mean, then power is pretty high. It's approaching 1. What this means is that if the mean has shifted, it's easier to detect if it's a large shift rather than a very gradual or small shift. If we bring this back to something like 0.2, and now we look at the effect of sample size. Sample size, remember these are sampling distributions. As you increase the sample size, you narrow the distribution. And in so doing, you bring up x bar c. X bar c actually goes to the right because that's underneath the null hypothesis. And what you're doing to beta is you're making it really small, and so you're also increasing the power. So as you increase sample size, you can increase the power of the test. And also, if the shift in mean is greater, you also have a higher power for the test. If we look at power graphically, and we look at the effect of the mean shift that we're trying to detect, the difference between mu naught and mu 1, as the shift in mean is greater, x bar c remains the same, and so alpha remains the same. As we increase the distance between the null and alternate hypothesis, beta will actually go down. So let me rewind that. We start with a very small mean shift. We increase it. X bar c remains the same. Beta is always on the right-hand side of x bar c. So the power increases when we have an increase in the mean shift. It also happens that as alpha is increased, the blue shaded area would become smaller. So type 2 risk also depends upon alpha, or the type 1 risk. Hopefully you learned a little bit more about power in this screencast. Thanks for watching.